Greetings, mechanics friends. Hope I ready to learn you are. Today we wish to harness the force method. However, if we want to achieve that learning objectives, first we must review. Learning objective number 1, identify statically indeterminate systems. Number 2, draw axial force diagrams for indeterminate systems. Number 3, solve engineering problems involving statically indeterminate systems using what we call the engineering toolbox. Thus, we will come to know how to solve indeterminate problems, and then we will look forward to harnessing the force method. If force method you want to learn, I recommend neat problem homework solving is must. I like to use engineering computation paper. Now, using engineering computation paper, we can try to harness the force method. Now, if we concentrate very hard, focusing on our engineering toolbox of equilibrium, kinematics, and material law, if we concentrate all that effort, we might just be able to harness the force. In order to apply the force method to a statically indeterminate system, we first have to define what static determinacy means. So if we look at the words, it just basically means that are we able to determine all the answers, so all the forces and deflections, using statics alone. So I want you to recall the equations of equilibrium for a 2D rigid body from statics. So I have here just a beam with a pin on the left and a roller on the right. And so you would draw a free body diagram something like this using our knowledge from statics. And we would then say we could solve for these different variables if we apply some forces in the x, some forces in the y, and some moments about the z-axis, at least for a two-dimensional structure. Now, being the learned mathematicians that I know you guys are, you would then say, okay, I have 3 equations of equilibrium, and I have 3 unknown variables, ax, ay, and by. I know if I have 3 linearly independent equations and 3 variables, then mathematically I'm able to solve for all my unknown variables. Therefore, we would say that this rigid body would be statically determinate because we are able to determine all of the variables using our 3 equations of equilibrium that we learned in statics. Now I want you to consider what happens if we add another support condition at point C. So now I've added another roller at point C. So I go ahead and I can sketch my free body diagram. So I still have AX and AY at the pin at A. I have BY at the roller and CY in the middle. I'm still a two-dimensional rigid body, so I still only have 3 equations of equilibrium. But now I have 4 unknown variables, 4 unknown support forces. Therefore, I won't be able to come up with 4 linearly independent equations. I'll only be able to come up with 3. And therefore, we would classify this rigid body as statically indeterminate because we will have to use something else beyond statics to determine the answer of the problem. Very simply put, we say a problem is considered statically indeterminate when the number of unknown forces exceeds the number of equations available from equilibrium. To further examine statically indeterminate problems, I want you to consider a one-dimensional bar subjected to an axial load. So I have this bar ACB with a load P applied at C. I know that to resist this load, I have some sort of reactions at A and B. And so I could sketch my reactions, AX acting to the left and BX acting to the left, because I'm guessing that both of the reactions are going to resist the applied load. Let's go ahead and take a look at a demonstration so we can better understand this. Now that we know how to identify statically indeterminate systems, let's go ahead and take a look at the force distribution in these members. So I have here my trusty lightsaber, right? I want to make this my 1D axial bar that we have here in our free body diagram. Now, I'm going to apply a force here in the middle, and it's going to be driving towards point B, which I'll take as being like a fixed end. On the other side, I have a fixed end at point A, and it's going to be grasping the bar. All right, as I apply the force directed at the wall, what do you think is going to be the reactions at points A and B? Well, if you're like me and you can harness the ability of the force method, you can probably just talk to inanimate objects. Well, we find out the wall is telling me that it has a reaction pushing against the force. And when I talk to my hand, it tells me that it feels a pulling. And I think that's to be expected, right? We have a force pushing towards the wall is resisting that force. My hand is also having to apply some sort of tension to prevent this from extending to too much. And so that gives us an idea of what the free body diagram would look like. Now, how much of this force is going to either side? Well, it's kind of hard to tell. We might say that since I applied the force in the middle in this particular video, then maybe half is going each way. And that would be true if these had the same geometrical properties as well as material properties. But what if I don't have the same, right? This is our lightsaber, this is our base. What if I apply the load off-center like we have in our notes? It's harder to tell how much force is going towards the wall and how much force is going towards my hand. But we probably can guess that together the wall and my hand have to resist the applied load. And we'll see that and we'll prove that when we write our equilibrium equation. Sum of forces in the x direction shows us if we take positive to be forces acting to the right, we have P minus AX minus BX equals 0. So we can rewrite this to say that AX plus BX will have to equal the applied load P, which is what we figured out in our demonstration. The other equations of equilibrium, some forces in the y and some moments about the z-axis, yield pretty much 0. Now I know it's a fixed end, and we could technically say that there are fixed end moments and vertical reaction at these points, but because we only have a horizontally applied load, we really don't have any forces in the y direction, and we won't have any moments. So now we have two unknown variables, but we only have one available equation from equilibrium. And therefore, we would say that this problem is then statically indeterminate because the number of unknown forces exceeds the number of equations we have available from equilibrium. All right, so how are we going to fight down these indeterminate systems and come up with a way of solving them? Well, we know that from statics, right? Statically indeterminate means we can't determine it using our statics alone. And so that means we're kind of in a pinch. But luckily, we're here in mechanics and materials. And so now we're going to have some sort of tool to solve this. I call this our engineering toolbox, and it's composed of 3 parts. So number 1 is equilibrium. Equilibrium is what we know from statics very well. The other 2 parts of our toolbox are called kinematics, or other people refer to this as compatibility. And then we have material law, or others call this constitutive law. Pretty much every problem out there, whether it's statically determinate or statically indeterminate, we can solve for forces and displacements in any kind of system with any kind of forces on it if we learn to apply these three tools. Now, sometimes the problems get large and intense. We'll be working here with just kind of the basic beginning indeterminate problems, but all the same, it's going to require a little bit of concentration and an openness to some new knowledge. Let's get at it. I hope you're as excited as I am to use our engineering toolbox. So let's talk a little bit about what that is. Equilibrium, number one, is what we know from statics. In equilibrium, we relate forces to one another in the system. And because we relate forces, we can therefore relate stresses, since stresses are related to the forces. In kinematics, we relate deformations in the system. So now we're talking about displacements or deformations. And since deformations are related to strain, that means we can also relate strains in our system to one another. So equilibrium relates forces back and forth. Kinematics relates deformations. And now we have to have some way of going between forces and deformations, or going between stresses and strains. We know that from our stress-strain test, we can, for a particular material, perform a test to show that relationship between force and displacement, or between stress and strain. So that is what we refer to as our third tool, material law. So material law relates our forces to our deformations, or our stresses to our strains. In the linear elastic range, we will use the material law sigma equals E epsilon, where E is the modulus of elasticity. If we want to relate forces to displacements, the equivalent is then Hooke's law, delta equals PL over EA. So we're going to jump into the next video and see how we can apply these three tools to solve an indeterminate problem. I hope you're not intimidated by the engineering toolbox, but just in case you are, I brought along a little friend here for some inspiration. You have anything to say to them? Engineering toolbox. Learn you must. Indeterminate problems, solve will you. Then we learn method of force.